We have one last example from this section of Lagrange multipliers, and this example is a situation where we are trying to max or min a function with two constraints. So before we said that you would just take gradient f, set it equal to lambda gradient g, where g was our constraint function. But now I'm telling you that we have two constraint functions. And this is not that difficult. It's not a big problem. In fact, we're just going to tack on an extra lambda gradient g. We're going to act like we're adding together two vectors to create gradient f. So we'll use something like, I can't remember what the textbook uses for their second. Oh, they just use subscripts. I don't like subscripts, so instead of using lambda 1 and lambda 2 like the textbook does, I'm going to instead use gamma. So we'll have gamma times gradient h. So we'll have two constraints, g and h. Each one gets its own Lagrange multiplier. So if we're trying to find the max and min values of the function f, subject to these two constraints, notice that these constraints are not both written so that they're equal to a constant. One is, one isn't. Let's go ahead and pick one to be g and one to be h. It really does not matter which one you pick to be which, but for simplicity, let's pick the first one to be g and the second one to be h. Now, in order for this first constraint to be g, we need to move all of the terms to one side. Right now they're on both sides. So instead of writing z squared equals x squared plus y squared, we need to write that as z squared minus x squared minus y squared equals 0. So that g is the function z squared minus x squared minus y squared. And then h, it's already equal to a constant, so h is the x plus y minus z plus 1. All right, now that we have f, g, and h identified, we'll find the gradient for each one. So gradient f looks like 2x, 2y, 2z. Gradient g looks like 2, went a little too fast there. Negative 2x, negative 2y, 2z. And then gradient h will look like 1, 1, negative 1. And then we'll separate the components. So the I hat component from f is 2x. That will be equal to lambda times gradient g, the x component. So that would be lambda times negative 2x plus lambda times the x component from gradient h. So that would look like lambda times 1. Then we'll have the j hat component from gradient f, that's 2y. Lambda gradient g, that would be lambda times negative 2y. Lambda gradient h, that would look like lambda times 1. And then we have our k hat component from gradient f, that looks like 2z. From lambda gradient g, that looks like lambda times 2z. And then from lambda gradient h, that would look like lambda times negative 1. And we can clean these up a little bit. So lambda times negative 2x, that could just look like negative 2x lambda plus lambda. Lambda times negative 2y, that could just look like negative 2y lambda plus lambda. And then this last one, we have 2z lambda minus lambda. Again, there's 4 unknowns here, only 3 equations, so we have to throw in, there's 5 unknowns here. Can you count them all? X, y, z, lambda, and gamma. So there's 5 unknowns, which means we need to add both constraints into this system of equations to solve. So we'll have z squared equals x squared plus y squared as one constraint, and x plus y minus z plus 1 equals 0 as our fifth equation. Solving a system of 5 equations with 5 unknowns can feel a bit overwhelming. And I'm actually not going to go into it here because that's not the point of this section. Although, technically, you should be able to solve this system. You've studied math for many years to be able to be in this class. So if this is something that you're afraid you can't solve, please reach out and ask for help either from me, a classmate, or some of the student service tutorials. But I just wanted to show you how this problem would be solved. So if you have multiple constraints, you fix that by just tacking on another Lagrange multiplier, pick whatever Greek letter you want, times the gradient of that new constraint. And then after this, the process is just like before with a single constraint. Solve the system, test all of your cases, and then you would plug your value back into the function to find the max or minimum values. If you are curious to see how this problem works out, check it out in the textbook. It starts on page 465. And it's a lengthy process to solve this system. So it starts on page 465 and it stops on page 468. I don't really have enough space on this one slide to solve it, so I'm going to stop it here and let me know if you have any questions. You're more than welcome to join me in an office hour to help work through this problem if you'd like.